So very good morning everyone. Just confirm me once whether audio video is clear to you or not. Just confirm it once. Just confirm whether the audio video is clear to you or not. Okay, so I welcome you all to the foundation course by IMS GATE Academy. We are studying about the basics of strength of material, and in the previous sessions we have seen basics of stresses, then thermal stresses, and then how to draw the shear force and the bending moment diagram. All these basics I am again reminding you will going to help you to solve the application based question that are asked in GATE examination or any other technical exam, right? So up till now, we know how to analyze any structure by drawing a shear force and bending moment diagram, okay? Now from today's session onwards, we will going to deal in a particular type of stresses, okay? In the beginning session, I told you that stress will come over the body when some deformation will happen over it, right? When you apply some external load over the body, this body will undergo some deformation. In order to restrain this deformation, the internal resisting force will develop, and this internal resisting force per unit area will be termed as stress, okay? This stress is directly dependent on the strain. Until and unless strain will not come on the body, stress will not develop inside the body. Is that clear? Right. Now after this we have discussed about types of stresses. So if we take the original area, it is termed as engineering stress, and if we take the actual area, it is termed as actual stress, okay? Today we will going to see one more classification of stress. So you can give the next heading, types of stresses. Types of stresses or types of stress. Now depending on the nature of stress, where the stress is actually acting and how it is acting, stresses are broadly classified into two types. First one is the normal stress, and second one is your shear stress. Okay. If the stress is acting perpendicular to the cross section, then that stress is known as normal stress. For suppose if this is my body, this is my body, I'll draw here. And this is the cross-sectional area of the body. Right? This is the body and this is the cross-sectional area of the body. If the stresses are acting perpendicular to the cross-sectional area, like this, if the stresses are acting perpendicular to the cross-sectional area, then this type of stress will be termed as the normal stress, okay? So if I draw this as the cross-sectional area, if this is my cross-sectional area, and the stresses are acting normal to the cross-sectional area or perpendicular to the cross-sectional area, then these type of stresses are termed as the normal stresses. This is my cross-sectional area, right? If the stresses are acting perpendicular to the cross-sectional area, then these stresses are termed as normal stresses, okay? On the other hand, if again I'll take some body like this, again I'll take this body, for this body, if the stresses are acting along the area, then these stresses will be termed as your shear stresses. If the stresses are acting along the area like this, if the stresses are acting along the area like this, right? If it is acting along the area, right, this stress is acting along this resisting area, then this stress will be termed as the shear stress. Is it clear? So basically there are two varieties of stresses. First one is the normal stress and second one is the shear stress. Normal stress will act perpendicular to the cross-sectional area and shear stress will act along the cross-sectional area. So if the stress acting is, so for normal stress is perpendicular to cross section, right? And here in shear stress is acting along the cross section. Stress is acting along the cross section. So if you look into this cross section, this stress will be acting like this. This is the stress which is acting along the cross section like this. This is the stress which is acting along the cross section. If you take this cross section, shear stress will be acting along the cross section. Or if you like to draw this sectional diagram of section XX or cross section XX will be like this. This is the shear stress which is acting along this cross section. Okay. So these are the two varieties of stresses. First one is the normal stress and second one is the shear stress. Now we will going to see both the varieties of stresses in detail. So let us give the first heading, types of normal stresses. Types of normal stresses. Types of normal stresses. So as we already know that normal stress will always be acting perpendicular to the cross section, right? The normal stresses are basically of two types. Direct normal stress, direct stress, and bending stress. So normal stress are of two types, direct stress and the bending stress. So let us see what do we mean by direct stress. Direct stress we have already seen. So if any body is loaded axially, means if you are pulling the body axially or you are compressing the body axially, then in that case, the stresses developed in the body will be direct normal stresses. Let us visualize this. For example, we have a body again like this. And over this body, you are applying one tensile force like this. This load is P. And this cross-sectional area is A, right? This load will going to develop the normal stresses which is perpendicular to the cross-section. And these normal stresses looks like this. These normal stresses will look like this. These are the normal stresses that are developed in the body like this. Like this, normal stresses sigma will be developed, and this sigma is equal to load divided by the cross-sectional area. If you look into this cross-section, this is the cross-section, this area A, this is the cross-section area A. And if you draw these stresses will be like this, perpendicular to the cross section. And this is the value of sigma. As you can see here, for the entire depth of H, the value of sigma is constant. For this entire depth of H, sigma is constant. Sigma is uniformly distributed in the entire depth of H for this cross section. So when the direct stress will come, direct stress will always come due to axial loading. Second, direct stress will be uniformly distributed in the entire section. From top to bottom, the value of sigma is constant. It is not changing, right? Now, direct stresses are of two types. If the load is tensile, the stresses developed will be tensile in nature. If the direct stress is compressive, then the stresses developed will be compressive in nature. And if I talk about the sign convention, tensile stresses are taken as positive and compressive stresses are taken as negative. So if I talk about sign convention, I'll write here. So tensile stresses are taken as positive and compressive stresses are taken as negative. I hope this is already known to us because this is one of the basic classification that we have. And this is my sign convention. Right? This is the sign convention of direct stress. So I hope you will not make any mistake in visualizing the direct stress, right? Direct stresses will be distributed in the entire depth H. Direct stress is a type of normal stress because the direct stress will be acting perpendicular to the cross-sectional area, okay? Now talking about the second type of normal stress, which is termed as the bending stress. So today's topic is all about discussing the bending stress. For now, just see how this bending stress is a normal stress. Just recall once the definition of normal stress. Normal stress is that stress which will be acting perpendicular to the cross section. Okay. So if I have a beam like this and over this beam, if I apply some moment, this beam will undergo bending like this. This beam will undergo bending like this. I think I should take some other color. This beam will undergo bending like this due to the moment. This is the bending of the beam that will going to happen due to this moment M, right? Now, if you observe this fibers, the top fibers, these top fibers are in compression and these bottom fibers are in tension, okay? So, if you draw the cross section for this beam, if this is my cross section for the beam, the top fibers are under compression. So, this is under compression and the bottom fibers are under tension like this. So, top fibers are under compression and the bottom fibers are under tension. As you can see here, when you look into the top fibers are getting compressed by this stress. And again, this stress is perpendicular to this cross section. This top fiber is getting compressed by this compressive stress and this bottom fiber are extended by this tensile stress. Both these stresses are acting perpendicular to the cross section, hence the bending stresses are termed as normal stresses, right? We have the full discussion after this. We will have full discussion after this. Why this is varying linearly, how to calculate the value of stresses. That is a different issue. What do we mean by this dotted line? Okay, just don't think about that, all these things right now. Right now, focus on that fact that this top fiber is getting compressed due to this compressive stress which is acting perpendicular to the cross section. And this bottom fiber is getting extended due to this tensile stress at this bottom fiber. And both these stresses are acting normal to the cross section. Hence, the bending stresses are termed as normal stresses. One more thing, in the entire depth of the cross section, the stresses are not uniform. means the stress value is not constant. It is constantly changing. Okay. So for bending stresses, it is a type of normal stresses. Stress value is not uniform. Stress value is not uniform. Is not uniform along the depth. Stress value is not uniform along the depth. Sign convention is same. If the stresses are compressive, then they are taken as negative, and if the stresses are tensile, they are taken as positive. Sign convention is still same. I'll write here. Tension is positive and compression is negative. So this is the basic sign convention for the normal stress and the bending stress, right? Talking about the shear stress, we will going to see the entire theory of shear stress in the upcoming sessions. Right now, today's session will be dedicated to the types of bending stresses and how these bending stresses are developed and how these bending stresses are calculated. Okay. So please give the next heading. After writing this, give the next heading bending stresses. Okay. So we will going to discuss about the different types of bending stresses, right? Give the heading theory of pure bending. Okay, we will be discussing about first of all what do we mean by pure bending, because the concept of bending stresses or the formulas of bending stresses are only applicable when pure bending is happening. So first of all, understand what do we mean by pure bending. Okay, I have drawn one example in front of you. I have drawn one beam. This beam carries 2-point load at a distance of A from end A and at a distance of A from end B. First of all, calculate the support reaction. I want you to draw the shear force and the bending moment diagram for this beam, right? Today we will going to do it directly without doing all the calculation. So if you look into this beam, this is a symmetrically loaded beam. So total load, this P and P, half and half will be distributed in both the supports. So this P will be distributed here for support A and this P will be here at support B. So if you calculate the support reaction, it is P and it is also P. If you take the summation of horizontal forces to be 0, then HA, that is the horizontal reaction at A, it comes out to be 0. Okay. So this is the support reaction. If I draw the shear force diagram for this beam, the shear force diagram will be something like this. So at point A, I have to move up by the amount of P. At point A, I have to move up by the amount of P, right? Then from A to this point, there is no load acting. So shear force diagram will be constant like this. Okay. This is P. Then at this point, I have to move down by the amount of P. So I came down by the amount of P. So again, I reach back to the 0 value. Again, from this point to this point, there is no point load acting. So up till this point, the shear force diagram will be 0. Okay. Then at this point, I have to again move down by the amount of P. So I'll move down by the amount of P like this. Okay. Then between this point and this point, no point load or no load is acting. Therefore, shear force diagram will be constant like this. Then at this point, I have to move up by the amount of P. Right. So this is my shear force diagram for this beam. So this is positive and this is negative. And this is P. Okay. Now try and draw the bending moment diagram for this beam. So this is my shear force diagram, SFD. Now try and draw the bending moment diagram for the same beam. So if you draw the bending moment diagram for this beam, so due to this load P, there will be the moment P into X, right? So my bending moment diagram will be this straight line with the positive slope, okay? Then after this point, if you consider section XX in between these two loads, right? So the total moment will be P into X minus P into X minus A, right? So you will get P into A as a constant value for this entire span. For this entire span, you will get minus P into A as a constant value. Then after this, when you write the bending moment equation, it will be closing like this with the negative slope. So this is the bending moment diagram and this bending moment diagram is positive. Okay. Now observe this very carefully. For this distance, I'll name this as C and D. This is C, this is D. So this is also C, this is D. This is also C, this is also D, right? For this span CD, the value of shear force is 0. So shear force for span CD, it is 0. Second thing is, the value of bending moment for this span CD is constant. Value of bending moment for span CD is constant. So obviously, if bending moment is constant, d by dx of bending moment for span CD will be 0, right? And this we can identify since the value of shear force is 0. There is one relation that d by dx of bending moment is equal to the shear force. Actually, there is a series of relation starting from deflection, then slope, then bending moment, then shear force, then intensity of loading, right? So if you want to know that relation, those relations are like this. If y is the deflection, then dy by dx is the slope, which is equal to theta. D theta by dx is equal to the bending moment, and d by dx of bending moment is equal to the shear force. D by dx of shear force is equal to negative times intensity of loading. negative times intensity of loading. So this is the relations between all the parameters. So basically what I can infer from here, that the slope of the bending moment diagram is equal to the shear force, right? The slope of the bending moment diagram is equal to the shear force. So if I need to calculate the maximum value of bending moment, I have to check at which point the value of shear force will equal to 0. All these things comes in the detailed analysis of the shear force and the bending moment diagram. So if you just keep these relations in your mind, from here you can identify one simple thing, and that is the d by dx, or that is the slope of bending moment, will always equal to the shear force. So wherever bending moment will be maximum, your shear force will be 0, right? Coming back to this scenario, if you observe this beam, for span CD the value of shear force is 0, and you only see bending moment happening in this span CD, and the value of bending moment is also constant for this span CD. That span of the beam where shear force is 0 and bending moment is constant, that span undergoes pure bending, right? Wherever shear force will not be acting, or the value of shear force is 0 and some non-zero value of bending moment is there, or some constant value of bending moment is there, then that beam will undergo pure bending. So when these conditions are there, then for span CD, or I will write span CD is under pure bending. Span CD is under pure bending. Span CD is under pure bending. And if I talk about pure bending can be assumed as that beam will undergo a bending in a kind of circular arc, right? That portion of the beam which is under the action of pure bending, that will undergo bending in the form of pure circular arc, right? So first of all, we talked about pure bending. What do we mean by pure bending? That portion of the beam which has the value of shear force equal to 0 and has the constant value of bending moment, that portion of the beam is said to be under the state of pure bending. Okay. Now, when the pure bending is happening over the beam, in that case, bending stresses will be developed over the beam, right? So the next topic of discussion is how these bending stresses are developed and how these bending stresses are evaluated, right? So the entire discussion will be for that span which is under the state of pure bending. After this, give the next heading, assumptions in the theory of pure bending. And these assumptions are very important. Assumptions in the theory of pure bending. So the first thing is, we will be only talking about the spans which are under the state of pure bending, right? And what do we mean by pure bending? For that span, the value of shear force will be equal to 0, or the value of bending moment will be constant. So if you take d by dx of bending moment, it will come out to be 0, right? The first assumption is material is homogeneous. First assumption is, I'll write these assumptions in short. First one is material is homogeneous. Isotropic and elastic. Material is homogeneous, isotropic and elastic. So when you look into this assumption means that anywhere in the volume of the material, the property of the material will remain constant. If you move in the entire volume of the material, the property of the material will remain constant. So anywhere, any point inside the material, in any direction, right, the property of the material will remain constant. It means that if I talk about the Poisson's ratio along x direction will be equal to Poisson's ratio along y direction will be equal to Poisson's ratio along z direction, and this will be equal to mu. So only one value of the property of the material will be given to us, and that value of the property of the material will remain constant for all the direction at all the points. Second and the most important point which is listed here, material is elastic, right? So we will be having this entire discussion when the material is under the elastic state. You remember when we draw the stress strain curve, we draw this proportionality limit, then we draw this elasticity limit or elastic limit. So the maximum amount of stress that can develop in the material due to bending will be under the elastic state, right? Means if you just unload the material, it will going to regain its original shape and size. So all that discussion for bending stresses is for elastic material, right? This is the first assumption. Second assumption, material is prismatic. Material is prismatic, or the cross section of the material is uniform along the length. So what do we mean by prismatic material? Cross sectional area is uniform, or cross sectional area is same, uniform or same, one of the same thing, is same throughout the length. Throughout the length. So for example, if you draw a cube like this is one cube if you have drawn. This is one cube like this, right? For this cube, you can clearly observe that the cross section of the material is same along the entire length. So this is my prismatic section. This is the section of length L, and area of cross section is A at the starting and also A at the end of the bar. Okay. So when the cross sectional area is same throughout the length, that material is said to be prismatic material. That cross sectional shape can be anything. It can be square, it can be rectangle, it can be triangular, it can be anything. But it has to be prismatic throughout the entire length, right? So cross sectional shape can be anything. Can be any irregular or regular shape. So normal shapes like square, rectangle, circle, triangle, pentagon, hexagon, all these are regular shapes. Similarly, you have some irregular shapes also. Till the time the cross-sectional area is not changing, or the cross-sectional shape is not changing from the starting till the end of the member, that member will be classified as the prismatic member, right? So this is the second assumption. Material is homogeneous, isotropic and elastic, and second one is your material is prismatic. The next is, the third assumption is loading will happen along the symmetrical plane, along the plane of symmetry. Loading will happen along the plane of symmetry. Now, what do we mean by plane of symmetry? Okay, observe this again. This is my material. This is the body over which the loading has to happen. For this material, this is the line, this is the center line, which is equally dividing this material into two equal halves. When the load is applied over this line, like this, right, this load will have a tendency to bend the beam. If this load is not applied, if I draw this top cross-sectional area, and this is the center line. Till the time loading is done over this center line, only bending will happen in the beam. But if any load is applied like this, if any load is applied like this, away from the center line, what will it do? It will going to try and twist the member. Just observe this. If any load is applied apart from the center line like this, right? If any load is applied like this, apart from the center line, it will try to twist the member. It will try to rotate the member, okay? So, the loading will happen along the plane of symmetry. This is the plane of symmetry. If any loading happens apart from the plane of symmetry, then that loading will cause additional twisting in the member. So, I'll just I'll write here load apart from or I'll write like this, load acting apart from plane of symmetry will cause additional twisting. No doubt bending will be there, but these loads will also cause additional twisting. Apart from plane of symmetry will cause additional twisting. Will cause additional twisting, right? The next and the fourth and the most important assumption is plane of loading. Okay, the cross-sectional area remains plane after loading. Cross-sectional area remains plane after loading. This is one of the most important assumption that I need to discuss here, because this assumption will going to tell us how the bending stresses are varying linearly from the different fibers. Okay, so I'll just draw this cross-sectional area. First of all, you consider this body like this. Okay, this is the body I have. As you can see here, for this body at different so this is my one cross section, right? This is my another cross section like this. And till now, no loading is done over this beam. When you apply the bending moment over this beam like this, when you apply the bending moment over this beam, when you apply the bending moment over this beam, for suppose this is the bending moment that you have applied like this, right? This bending moment will try to bend the beam like this, and you will going to have the sagging shape of the beam. You will going to have this kind of sagging shape of the beam. This is the sagging shape of the beam. Or I'll draw this neutral axis first. So this kind of sagging shape of the beam you will going to have, right? If you take these cross section, which were this drawn in green, these cross sections are like this now. And these cross sections are still plane even after bending. These cross sections are still plane even after bending. Earlier they were like this. Now due to bending they have tilted like this, but they are still plane in nature. So this is what we mean by the cross-sectional plane remains plane, the cross-sectional area remains plane after bending, right? This cross-sectional plane will not be distorted. They will remain plane even after bending. So if you just observe this top fiber is getting compressed by somewhat amount. This bottom fiber is getting elongated by somewhat amount. But there is one fiber, this fiber, as you can see here, this fiber is neither getting elongated nor getting shortened, right? This fiber, the length of this fiber remains same. So that fiber for which the length remains same is termed as neutral axis, right? Is termed as neutral axis. So this is my neutral axis. This is my neutral axis NA. What is the property of the neutral axis? Neutral axis does not undergo any elongation or any contraction in the state of pure bending, right? So if you observe this sagging moment has caused compression in the fibers above neutral axis, and it has caused tension in the fiber below neutral axis. But at neutral axis, there is neither contraction nor extension, right? So above neutral axis, it is compression, and below neutral axis, it is tension. And if I talk about compression, the fibers will contract. Fibers will contract. And for tension, fibers will elongate. Fibers will elongate. And for neutral axis, there is no change in the length of the fiber. For neutral axis, there is no change in length. This is for neutral axis, right? So it is pretty much clear that whenever you apply the bending moment over a beam, and if this beam undergoes bending, then neutral axis will not change the length. If this is a sagging moment, then all the fibers above the neutral axis will be under compression and all the fibers below the neutral axis will be under tension. The fibers which are above the neutral axis will contract, they will change their length. and the fibers below neutral axis, they will elongate or they will expand, right? Now, if you plot the strain distribution along the height of the member, that strain distribution will be something like this. Okay, 1 minute. I'll take this. And this is my cross-sectional area. Okay. Now observe this. This neutral axis will not show any change in length, right? So this neutral axis has the zero value of strain. Since delta L, that is the change in length for the neutral axis, 0. So the value of strain for this neutral axis is also 0. So I am again drawing this neutral axis. This is my neutral axis like this. So this is my neutral axis, right? Okay. These fibers are under compression. So they are reducing, right? The change in length is negative. For these top fibers, their delta L is negative, right? Their delta L is negative. If delta L is negative, then the strain will be also negative, and these strains will be plotted like this, right? So this is the strain that is happening in the top fiber. And this strain is keep on reducing, since as you can see here from the plane, right? This top fiber is under more strain, then strain is constantly reducing from top fiber till the neutral axis. So this strain keeps on reducing like this. This strain keeps on reducing like this, right? This strain keeps on reducing like this, and it is equal to 0 at the neutral axis. So this is your compressive strain or negative strain. This is your negative strain. This is your negative strain. I'll just erase this. This is your negative strain, and this is your absolute compressive, which is the maximum compressive strain. Similarly, this strain is tensile or positive below the neutral axis. So this is positive below the neutral axis, and it keeps on increasing till the bottom fiber. So this is the value of strain till the bottom fiber. So this is positive and this is epsilon T. And this is how your strain gets varies from top fiber till bottom fiber. So this is your strain distribution. This is your strain distribution diagram. From top fiber till bottom fiber, this is how your strain is varying. As you observe from this diagram, at neutral axis, there is no change in length, therefore strain is 0. At the top fibers, the strain is negative because of the compressive stress. At the bottom fiber, the strain is positive due to the tensile stress, right? Now, if I have to draw the stress diagram from this strain diagram, how can I draw? So I know this stress is equal to E times of strain, right? And it is a kind of a linear relationship. Stress is directly proportional to strain. So if strain is varying linearly, you will going to have same variation for stress also. So again, if I draw this stress and strain diagram, so this is my value of strain that I have drawn. Okay. This is epsilon C and this is epsilon T. This is negative and this is positive. This is strain distribution. From this strain diagram, if I have to draw the stress diagram, one thing is clear that stress is equals to E times of strain. So E is constant, E is the Young's modulus. So same variation you will observe for stress. Same variation you will observe for stress, right? Like this. This is your stress variation. This is your sigma C compressive stress and this is your sigma T tensile stress. These stresses will be acting like this. So over the cross-sectional plane, you can clearly see if this is my cross-sectional plane, these stresses are acting perpendicular to the cross-section. If this is my cross-sectional plane, these stresses are acting perpendicular to the cross-section. The compressive stress will try to contract the member and the tensile stress will try to elongate the member. So this is how your variation of stresses will happen for bending. So this is your bending stress distribution. This is your entire bending stress distribution for a beam, right? And this bending stress varies linearly from the top fiber to the bottom fiber. And at neutral axis, the value of stress is 0. So I'll write here, bending stress varies linearly bending stress varies linearly along the depth next at neutral axis, bending strain is 0 and bending stress is also 0. At neutral axis, bending strain is 0. Bending strain is 0. And also bending stress is 0. Right, so these are the assumptions in the theory of pure bending. This assumption is very important that plane section remains plane after bending. That will going to tell us how the strains are developing in the cross-sectional area. So if this is the initial plane, after bending this plane shifted like this, right? This plane got this slant. And this is the amount of strain that are developed in all the fibers of the cross-section. At neutral axis, there will be no elongation or no shortening of the fiber. But if compressive stresses are developed, then those fibers will be contracted, and for tensile stresses, those fibers are extended, right? Now give the next heading, equation of pure bend. Okay, before that, how to calculate the depth of this neutral axis? How to calculate this depth of neutral axis? How to calculate this depth of neutral axis y bar, right? So we will discuss on that also. For different sections, we will going to discuss how to calculate the depth of neutral axis. So give the next heading, depth of neutral axis or calculation for depth of neutral axis. Calculation of depth of neutral axis. Because position of neutral axis is very important, as you can clearly see from these two diagrams that without knowing the positions of neutral axis, we cannot compute the value of bending stresses at different fibers. This neutral axis is used as the basis to locate the fiber, and once we know the position of the fiber, then to calculate the bending stresses developed in those fibers. Okay, so the position of neutral axis is very important to calculate. So next topic of discussion is calculation of neutral axis. So this neutral axis will always lie at the centroid of the cross section. As simple as that. Neutral axis will always lie on the centroid of the cross section. So neutral axis will lie on the centroid of the cross section, on the centroid of the cross section. As simple as that. No matter whatever will be the shape of the cross section, for that cross section, wherever will be the position of centroid, at that point your neutral axis will going to lie, right? So neutral axis will always going to lie on the centroid of the cross section. Neutral axis will always lie at the centroid of the cross section. So if this is my cross section, if my cross section is rectangular like this, so this is B and this depth is D, and I need to locate the position of the neutral axis. Neutral axis will lie at the centroid of the cross section, and we know that the centroid for rectangular section will be at a depth of D by 2 from either of the fibers. So either at the bottom fiber or at the top fiber, the position of the CG will remain same. This is D by 2, right? So from wherever you want to locate the position of neutral axis, either from the top fiber or from the bottom fiber, you can locate the position of CG, right? So this will be my neutral axis. This will be my neutral axis. Neutral axis will always pass through the CG of the cross section. Similarly, if I have a triangular section like this, if I have a triangular section like this, right? For this triangular section, this is my CG. So my neutral axis will pass through the CG like this, right? This will be my neutral axis. And if I want to locate the position of the neutral axis, so if h is the height of this triangle, so this neutral axis will be at a distance of 2h by 3 from the apex, 2h by 3. This is known as the apex of the triangle and this is known as the base of the triangle. And this CG will be at a distance of h by 3 from the base of the triangle. Right? 2h by 3 from the apex and h by 3 from the base of the triangle. And this is the neutral axis. Okay. So neutral axis will always lie at the CG of the cross section. Similarly, if I have one square cross section like this is my square cross section. Now it is very easy for you to tell us where the position of neutral axis will be there. If A and A are the sides of a square, the neutral axis will always pass through the CG of the cross section. This is the CG of the cross section and this position is A by 2 from the top fiber and A by 2 from the bottom fiber. So all these things should be known to you. At least for the basic figures, you can directly have the value of neutral axis. But when some complicated figures are there, okay, then in that case, we need to calculate the position of neutral axis. That we will going to see just now. First thing, if any symmetrical figure is there, then location of the neutral axis will be the midpoint. As you can see here, this rectangle is the symmetrical figure. So the CG will add the midpoint of this depth. Similarly, if you look into this square is again a symmetrical figure. So for this square, the position of the neutral axis will be at the position of the CG will be at the mid height of this square, right? So mid height is A by 2. Similarly, if I draw few of the cross section in front of you like this, if I draw one I section, or before that, if I draw one circle, this I forgot. If I draw one circle, obviously the CG will lie at the center for this circle. So if the radius of this circle is R, then from the top fiber or bottom fiber, the neutral axis will lie at a distance of R. This is R. This is R, right? So these two will be the position of neutral axis NA. Now talking about the symmetrical figures, right? So the first symmetrical figure is I section. First symmetrical figure is I section. Okay, so this is the I section that I have. For this I section, the width of top flange and the bottom flange is same. The width of top flange is B and the width of bottom flange is also B. So this is B and this is also B, right? Both the flanges are of same width. Since this section is symmetrical about this line, hence CG will also lie at this line. And this CG or this line will be the axis of symmetry. And if this is the axis of symmetry, it will exactly lie at the midpoint of this entire depth. If the entire depth of this I section is D, then this CG will lie at a distance of D by 2 from the top fiber and D by 2 from the bottom fiber. So this distance is D by 2. If total depth is D, so this distance is D by 2 and this distance will also be D by 2. This distance will also be D by 2, right? So like this, whenever any symmetrical figure is there, CG will always lie at the axis of symmetry. And this axis of symmetry will be also called as the neutral axis, right? Okay, I'll draw this figure in front of you. First of all, tell me, How many axes of symmetry are there for this I section where top and bottom flanges are of same width? So one is this section, this is symmetrical. The another one is this section. This along this section which is perpendicular to this, right, and it is passing through the CG. This is also dividing the cross section into two equal halves. So this will also be the axis of symmetry. Now talking about some irregular figures. Okay, so let us draw some irregular figures. This is the irregular figure, right? This is the irregular figure. If you look into this axis is not dividing this cross section into two equal halves. Okay. So we need to calculate first of all the position of the neutral axis. Wherever we cannot get the axis of symmetry, right, there we need to calculate the neutral axis. So we need to find that CG, we need to locate the position of the CG for this cross section. For that we will need some dimensions. So this is say 80 mm. Sorry. So this is 80 mm. This is 20 mm. This is 60 mm. This distance is 10 mm. Then this is like 30 mm or 40 mm. And this is 100 mm. Right? So we need to locate the position of the neutral axis for this cross section. Okay. Anytime you need to find the position of the cross section, position of the neutral axis, you need to take the weighted average. Okay. Now, how to get the weighted average? First of all, in this cross section, you can see the three rectangles. First top rectangle, then this rectangle, then this rectangle. For this top rectangle, CG will be at this distance, and this distance is termed as Y1 bar. What is Y1 bar? Y1 bar is the CG, position of the CG of the top rectangle from the top fiber. And what is the value of Y1 bar? Y1 bar will be equal to 10 mm. Half of 20 mm will be 10 mm. So Y1 bar will be 10 mm. Okay. So if you look into this rectangle, the area of cross section for this rectangle is A1, and A1 is nothing but 80 mm into 20 mm. So 80 into 20. And this is mm square. This is mm square, right? So this top rectangle is done. This is my rectangle 1. Now talking about second rectangle. This second rectangle will have the CG here, and this CG will at the midpoint of this height of 60 mm. So this distance is 30 mm. 30 plus 20. So this Y2 will be, Y2 bar will be, this is the Y2 bar. And this Y2 bar will be 30 plus 20 mm, that is 50 mm. So Y2 bar is 50 mm. Okay. Tell me what is the area for this rectangle? Area for this rectangle is 60 mm by 10 mm. 60 mm into 10 mm. So this is 60 into 10 mm square. So this is my A2. Okay. Now coming to this third rectangle. So for this third rectangle, the CG will lie at the mid height of this rectangle, and the mid height of this rectangle will be 20 mm. This distance will be 20 mm. So if I have to locate the value of y3, so y3 bar, I'll write here. This is y3 bar. This is y3 bar. So y3 bar is this is 20 mm, 20 plus 60, 80, 80 plus 20, 100. So y3 bar is 100 mm. Right. Now what is the area for this rectangle? Area for this rectangle is 100 into 40 mm. Area for this rectangle is 100 into 40 mm. So A3 is 100 into 40 mm square. Right. So this is the detail that we have. We have the value of y1 bar from the top fiber, then y2 bar from the top fiber, and y3 bar from the top fiber. Okay. Now good afternoon, a very good afternoon. Now we what do? We actually assume one position of neutral axis. I'll assume one position of neutral axis. Say this is my assumed position of neutral axis. So this is my assumed position of neutral axis. This is my assumed position of neutral axis, this one, right? And this is the neutral axis that is there. This is the assumed position of neutral axis, and this neutral axis is at a distance of y bar from the top fiber. This is at a distance of y bar from the top fiber, right? Now, how to get the value of this y bar? That is the CG. So, y bar is the weighted average of all these areas with respect to the distance from the top fiber. Or simply, if you take the moment of all the areas about this top fiber, so moment of all the individual area about this top fiber will be, first of all, if you take the moment of this area A1 about this top fiber, so it will be equal to A1 into Y1 bar. So taking the moment of area, about top fiber. So first moment will be A1 into Y1 bar. So you have A1 Y1 bar, right? Second moment will be this A2 into Y2 bar. Second moment will be A2 into Y2 bar. Third moment will be this A3 into Y3 bar, right? This is A3 into Y3 bar plus A3 into Y3 bar. And this entire moment should be equal to the moment of this entire area about the CG. So if you need to calculate the moment of the entire area about the CG, it will be A1 plus A2 plus A3 multiplied by Y bar. So this should be equal to A1 plus A2 plus A3 into Y bar. Okay, so this can be written as Y bar is equal to A1 Y1 bar plus A2 Y2 bar plus A3 Y3 bar divided by A1 plus A2 plus A3. A1 plus A2 plus A3, right? And this is how you can calculate the moment of area. Because we know that moment of area about the CG will be equal to the individual moment components of the area, right? Just substitute the value. So you have Y bar is equal to A1 is 80 into 20 and Y1 bar is 10. So 80 into 20 multiplied by 10. plus A2Y2. A2Y2 is 60 into 10 into 50. So this is 60 into 10 into 50 plus A3Y3 bar. A3 is 100 into 40 and Y3 is 100. So this is 100 into 40 multiplied by 100 divided by A1 plus A2 plus A3 divided by A1 plus A2. A1 is 80 into 20. Just do the calculation. A2 is 60 into 10 and A3 is 100 into 40. This is 100 into 40. Right? Just do the calculation and get me the value of Y bar. So this is 16,000 plus divided by so 71.935. Y bar is 71.935 mm. This is your Y bar, right? This is the position of your neutral axis from the top fiber. If you locate the total height, so this is 20 mm, 20 plus 60, 80, 80 plus 40, 120 mm. So this is total is 140 mm. Y bar is 71.935 and this distance will be 120 minus 71.935. So this is how you need to calculate the value of your position of neutral axis whenever asked in the question, right? So what you have to do, you have to take the moment of individual areas and you need to equate it to the moment of total area about the centroid, right? So it doesn't matter whatever shape is given to you, you can very easily calculate the position of the neutral axis. For suppose any T section is given to you, okay? For suppose any T section is given to you. Like this, you need to calculate the position of neutral axis for this T section. You need to locate the position for this neutral axis, right? I'll quickly give you the dimensions. Just try this question. So this is like 80 mm. This is 20 mm. This is also 80 mm. And this is 20 mm. You need to locate the position of the neutral axis for this T section. Just try it quickly. First, locate the value of Y1 bar. Second, Y2 bar. And then take the moments. Right? So if you look into this T section and if you need to calculate or locate the position of the neutral axis, we will always locate it from the top fiber. I used to do this from the top fiber, right? It's totally on you. If you feel like, you can also calculate from the bottom fiber, it doesn't matter. If you need to calculate the location of the neutral axis from the bottom fiber, then you have to measure Y1 bar and Y2 bar from the bottom fiber. Is it clear? So first thing is, if you have this triangle, for this triangle, this is the CG and this distance is Y1 bar. This distance is Y1 bar. What is Y1 bar? Y1 bar is half of this 20 mm, that is 10 mm. So Y1 bar is 10 mm. A1 area, this area of rectangle is 80 into 20. So this is 80 into 20 mm square, right? Now, coming to this rectangle, bottom rectangle. Bottom rectangle, this is the CG and this CG will be at a distance of 40 mm. That is half of this 80 mm. This is 40 mm. So the position of this CG from the top fiber will be 40 plus 20, that is 60 mm. So this will be 60 mm. This is 60 mm. So this is Y2 bar and this Y2 bar is 60 mm. And again A2 is 80 into 20. So A2 is 80 into 20 mm square. Right? So you have Y1 bar, you have Y2 bar. Just arbitrarily locate the position of the neutral axis. So I'll assume that my neutral axis is lying somewhere here, right? And this is the neutral axis and it is lying somewhere here. The position of the neutral axis is Y bar. The position of the neutral axis is Y bar. The position of the neutral axis from the top fiber is Y bar. This is neutral axis and it is at some distance Y bar from the top fiber. Now what you have to take? You have to take the moment of all the areas. Then you have to equate it to the moment of the entire cross-sectional area about the CG. This is my CG. So take the moment of areas. Take the moment of areas about the top fiber. About the top fiber, right? So first area is A1 and for this area A1, moment of area about this top fiber will be area A1 multiplied by Y1 bar. So first one is A1 into Y1 bar plus this second area is A2 and this into Y2 bar. So moment of the second area is A2 into Y2 bar. Right, and this should be equal to the total area of cross section, which is A1 plus A2 multiplied by this Y bar, and this should be equal to A1 plus A2 into Y bar, right? So if you need to calculate the value of Y bar, just substitute all the values of A1 and A2 and get the value of Y bar. So Y bar is A1, which is 1600, Y1 is 10, A2, which is again 1600, Y2 is 60, divided by A1 plus A2, that is 1600 plus 1600, right? So if you take 1600 common, so you are left with 10 plus 60. So 10 plus 60 is 70. Okay. Take 1600 common from the denominator also. So you have 1 plus 1, 2. 1600 and 1600 will going to cancel out and you will going to have 70 by 2. So 70 by 2 is 35 mm. So Y bar comes out to be 35 mm. So Y bar comes out to be 35 mm. So this is how you can calculate the position of neutral axis. It doesn't matter if you are calculating it from the top fiber or bottom fiber. The point is you need to get or locate the position of this neutral axis. Then only using this basis we can get the position of different fibers for calculating the bending stresses. So I hope this concept is very much clear to you. Again, I would like to repeat this. If you want to have the position of neutral axis from the bottom fiber, then this Y2 bar and Y1 bar should be measured from the bottom fibers, right? Here I have got the position of the neutral axis from the top fiber. That's why I have measured Y1 bar and Y2 bar from the top fibers, okay? So I hope you find this session very much informative in drawing your conclusion towards the bending stresses. And I hope you have understood where exactly we discuss about the position of bending stresses. So anywhere in the beam, wherever your shear stress is 0 and bending moment is constant, there will be, in that span only, you will going to have pure bending. And if the beam is under the state of pure bending, there we discuss about the entire theory of pure bending, right? So this is just the first part of pure bending. In the next session, we will going to discuss about how the bending stresses are developed and how to calculate the value of bending stresses for different fibers. So this is all for this session. Thank you so much for listening patiently. Have a very good day. Thank you so much.